Hello and welcome back to the virtual observatory of the gaia-clim project. I will now demonstrate how you can look at actual co-located data. You can access that panel, that functionality either by clicking onto the VO in the puzzle piece in the center, or by selecting data selection up here. You then get to the main menu for looking at observational data. On the left hand side you can choose the essential climate variable product that you're interested in. The demonstrator shows brightness, temperature, humidity, temperature, aerosol optical depth and ozone. I will choose ozone in this tutorial. Reference instruments, there are NDACC DOAS instruments that measure in the UV vis, the scattered light, or we can look at FTIR spectrometers that use the direct sunlight, or we can look at ozone sondes. I will choose here the FTIRs, and then we can choose a matching satellite product. In this case we have chosen GOM2, and we can either choose all the GOM2 instruments or pick a specific one. I will just choose one here. Then this is not backed up by NWP simulations because NWPs do not do ozone. This is more interesting when dealing with temperature and water vapor. Then we would pick a site that we're interested to look at. I might just choose Eureka for now. Eureka has quite a decent observation record. We could further narrow down the time series, which we may do at a later stage. We could also select certain time during the day that would make sense with a DOAS instrument that either operates at sunrise or sunset with some diurnally active chemical components of the atmosphere. You do have a diurnal cycle, so you may want to distinguish between sunrise and sunset. For the FTIRs, this is not really sensible to do, so we'll just take all the daytime observations we have. The maximum distance that we would allow in the co-locations, by default what is in the database, we allow a maximum distance of 500 kilometers and 6 hours. Now we can reduce this a little bit just to make the number of observations a little bit smaller. So at the moment we have 4,600 observations in those 9 years of observations. We could say instead of 500 kilometers we might go to 300 kilometers and maybe 180 minutes. In time difference between the two observations is our user chosen co-location criterion, and then you will see immediately that now there's only 1,355 observations left that fulfill the somewhat stricter co-location criteria. All the FTIR measurements are by definition cloud free, otherwise the instrument doesn't work. So we just hit the send data request, and then we are querying the database and will be presented with a quick plot. This will take a moment because we're just on a small test server that does not have an awful lot of horsepower. But okay, here we go. Over here you can see the individual measurements being listed, the individual co-locations. For example, the first co-location was taken on the 16th of May 2007 at Eureka, and the co-location had a distance of 78 kilometers between the reference observation and the satellite observation, and a time difference of just over 2 hours, 126 minutes here. And you can go from you can actually go through the individual observations if you wanted to, and for each of one of them you presented with the difference in time and space. Now I will actually just click this little button here in the middle so we get a bit more real estate, and the actual plots that we're interested in become somewhat bigger. We can see a little bit more. As noted up here, all the uncertainties are representing one standard deviation, so it's 1 sigma only. And I will scroll down a little bit more so we can see a little bit more towards the bottom. The left hand panel shows us the total amount of ozone in Dobson units as a function of time, so it's a time series of about 9 years. We see in blue the GOM observation, so the satellite derived total column amount of ozone, and in orange we see the one seen by the ground-based reference instrument, the FTIR. And on top of that we see some error bars, so actually we don't see very much of the GOM measurements. And in here we also have two lines, so we have the blue line representing the mean value for the GOM2 instrument, and in orange the one for the FTIRs. And we can see here, if I get the mouse, so the agreement is extremely well here, so there's a bias of, well, 1.8 Dobson units, or even less than that. That's much less than 1%. So this is a pretty good agreement for this type of validation work. If you move your mouse over it, you will get the individual values being presented to you. We will do that again when we zoom into it. And on the right hand panel we can see the uncertainty budget, and here we can see in purple the individual co-locations and how much they agree or disagree. So we see some outliers that disagree by almost 20%, or some outliers close to 30%. So here the difference is in percent relative to the reference observation. But we also see that this the differences are quite evenly spread either way of the x-axis, and we see the distribution in time. Also we see a shaded area here, an orange and a yellow one. The yellow one shows the total uncertainty budget, and in theory everything should be within these this envelope. In practice we see that that's not the case. That tells us that either our error budget is incomplete, which we think it is not, or the way we propagate the different error components, we have made some assumptions that are not realistic. And that seems to be the case because you use the root of square laws for all the relative uncertainties and the systematic uncertainties, and it looks like we rather have to add some of them outside the square, which will make them much bigger. Now, to play with this data a little bit, I will actually quickly go back and select a smaller time frame, just so we can work with it a little bit more, maybe somewhere here in this 2014 area. If we take just 2014, then it'll be a bit snappier in responding to our reactions. So we just go back to the form, and now we select a date here, and if we just click the year twice, then we can go straight to the year. And we said, well, we maybe pick from February 1st to 2014. Just go back 14 November. It's probably good enough at that high latitude, and just plot that. We already can see here that now we have only about 100 data points, so that's much quicker to work with, and also it responds much faster. Again, we click on this little symbol to get a bit more space, and then we can actually look at individual measurements in here. So we could say that on the August 4th 2014 at 1:30 in the afternoon, we have 352.6 Dobson units measured by the satellite and only 298.8 by the ground-based one. So it's quite a big difference, while on other occasions the agreement may be actually a lot better. Over here now, the interesting thing is to look at the error budgets. So we're looking at the NDACC FTIR. The first drop-down list here will allow us to choose the inner, the orange shaded area. At the moment we're looking at the relative total systematic uncertainties. Okay, but we can look at all the components that make up the error budget. The error budget is made up by the smoothing uncertainties, of either instrument, a smoothing bias of either instrument. We have random sampling mismatch uncertainty, which will depend on the difference in time and space, which is based on a simulation of the actual variability of ozone for that latitude and that month. We have the actual uncertainty, the random uncertainty of the measurement for either instrument, the systematic uncertainty of either instrument, so that we have things like uncertainties in the spectroscopic database maybe. And from there we can derive a total random measurement uncertainty and a total random uncertainty and total systematic uncertainty, and finally a total uncertainty budget taking everything into account. Now the interesting thing I think is more, well, maybe the random sampling mismatch error. We could look at that. So how much actually of the total error is due to mismatch in the co-locations, and here we can see quite a bit of difference. So if we were to look at this one, we would tell that it's probably a much closer match in time and space than some of these measurements. So they depend on these differences in space and time, and give the outer envelope also its little kings here. Now if we say, well, relative to the total budget, how much is due to random measurement uncertainty? And then we see that actually that is quite a small contribution to the total error budget. So you can play with this and get a feel for the different components of the total error budget, how important they are for this particular data set. And that's quite valuable. You can also, zoom in. Just if you hold down the left mouse button, you can just select an area, and when you just release the mouse, it'll zoom in. You only see this small area. You can also see now at this scale that the actual time difference, because the two, if they don't coincide in time exactly, then of course on the time axis you see a small difference between the overpass of the satellite and the ground-based observation, and that will find its way also into the error budgets. You also have couple of plotting and printing options in here that we will look at separately. This pretty much concludes the example for ozone, and I hope I can welcome you back for some of the other ECVs. Thank you.